going to conduct the workshop of running databases on Kubernetes. It's arranged by Kubernetes Community Days, Bangalore. So here is a brief introduction about me. I'm Fahim, lead software engineer at AppScot. Currently, I am leading the project called KubeDB. So KubeDB is a Kubernetes operator that makes it easy to provision and run databases on Kubernetes. You can easily manage your databases on Kubernetes using KubeDB. I've been working with Kubernetes since 2018. Okay, so here is the agenda of our workshop today. First, I will give a brief introduction to Kubernetes. I hope everyone here already knows about Kubernetes, but I'll still give a brief introduction. Then we'll try to answer the question, should we even run databases on Kubernetes? We'll try to answer that. Then we'll explore the options to run databases on Kubernetes. Then we'll give a hands-on demo of using the operator. We'll run a database on Kubernetes and we'll try to do some day 2 operations on that database. Finally, we will end our session with a question answer session. If you have any question in the meantime, you can always ask on the Zoom chat. So let's start. So what is Kubernetes? Kubernetes is a free and open source technology. It's a production ready technology. It makes it easy to automate your deployment and scale your deployment, management of your application very easy. Kubernetes was first released in 2014 by Google. There are many advantages of using Kubernetes. You can easily manage your containerized application. So if you have the application, then you can easily deploy it in the Kubernetes and you can easily run it there, and people will be able to use it from there. And you can easily scale your application as needed. So if you need like 3 replicas of your application so that it runs properly, or you need to scale it to have more memory or more CPU, or you need more storage, you can do it all in Kubernetes. Also, Kubernetes is cost saving than other solutions. You can pretty much manage everything. So you can cut costs yourself. You can run many open source software, etc. And Kubernetes is highly flexible. You can actually run Kubernetes on on-prem or on cloud. You can run, if you have some VM, you can spin up a cluster very easily. Kubernetes also helps you to avoid vendor lock issues because you are not actually bound to any vendor. You can use any open source software, any software you like when you are using Kubernetes. Also, Kubernetes offers various storage options. So you can use your own storage, or you can use any cloud storage, etc. Kubernetes allows you that. Also, there are very different kind of storage options, like you can expand your volumes, or you can take snapshot, etc. All of that that's supported by Kubernetes. Also, another important thing is it has a large community. So if you have any problem, you can just go to the community and you will definitely get your answer. So we'll try to see the components of Kubernetes. First is the cluster. So what is cluster? The Kubernetes cluster is a collection of machines or servers, which actually helps you to aggregate the resources. Like you have 3 servers, and each of them has a different kind of RAMs, different CPU, different disk sizes. With Kubernetes, the cluster enables you to use the CPU, RAM, disk, and aggregate them and use it for your different kind of application. So when you are running Kubernetes, that means you are actually running a Kubernetes cluster. Then there is a concept called node. We talked about the collection of servers. The servers are actually called node here. That's the main component of a cluster. They are just working machine. They can be virtual machines or they can be physical machines. Also, the pods actually runs here in the nodes. The pod actually can run a Docker container. Docker runtime. So pod actually run their container in those Docker environment. Node also runs the kubelet. The kubelet actually used by the node to communicate with the control plane. So the node actually connects with the control plane and gets the command to schedule pods here. Also, there is a concept called namespace. It's just nothing but a logical environment for your applications. Using namespace, you can scope access to your cluster. Like you want to use monitoring, you want to use the application. So you are just logically dividing your cluster into different pieces. So you are using one environment for your monitoring apps, one environment for your actual apps, one environment for your database apps, etc. And the main thing about Kubernetes is pod. The pod are the main atomic unit of Kubernetes. So when you are running your application, that means you are running it on a pod. So pod are nothing but a collection of containers. It can have one container or more containers. The pods are actually runs on the node that we have explored before. So the pods actually have multiple containers or one container that runs in the node's Docker environment. Also, the containers in the pods can share resources like storage and networking, etc. So suppose you have two containers. One container generates a certificate. You need the certificate in another container. So you can actually share the certificate via shared volume or storage, and you can use that from another of your container. Also, you can share networking, like you can communicate via the containers. So it makes it easy to run things on pod. Then there is deployment. In Kubernetes, user doesn't actually run pod directly. They run it via deployment or stateful set. So what is deployment? Deployment is a resource that controls the behavior of the pod. So in the deployment, you just provide your declarative updates, declarative specification of your application. Then the deployment creates the pod from the specification. So deployment enables you to describe your application lifecycle, like you want to give a health check to your application. You want to check periodically that your application is working perfectly. So you can do that via deployment. Also, you can have multiple replicas of your application. So to do that, deployment actually creates a resource called replica set. That replica set actually responsible for creating the replicas. It manages the replica. Then it's mainly intended for stateless application. The application that doesn't have any state. So you have multiple instances of your application, but there doesn't maintain any state. So you can use that for a stateless application. It is very popular resource for running stateless application. Also, pods are interchangeable. That means the pods have same specification, and if you connect on one pod or doesn't matter on another pod, you will always get the same result because they are interchangeable. Also, there's another thing, they don't have a definite ID or a specific ID. So so they are interchangeable. Then there is the thing of stateful set. So we have talked about deployment. Stateful set is similar to deployments. Just it is similar to deployment. It controls the behavior of the pod. But deployment is for stateless application. But stateful set is for stateful applications. So for running database, we actually need the stateful set because database itself is a stateful application. the main difference from deployment is pods are unique and they are not interchangeable. They have a persistent ID, so you can have a DNS name for them, a specific DNS name for each of the pod. Also, each pod has its own volume, can have its own volume. So they can have its different volume, but in deployment, you cannot have different volume for different pods. And there is the concept of service. Service is nothing but a logical abstraction of a deployed pod. A service can actually select multiple pods and route its network query to the specific pod. So you can connect a set of pods by a service name. It provides routing and discovery between pods. So you can actually connect with service to a pod or different pods. There are different types of services like cluster IP. With cluster IP services, you can actually connect to the ports only in a cluster. Then there is node port services. It exposes
ठीक है मत करो उसमें क्या है कल कर लेना
it exposes a node on each of the it exposes the port on each of the node. So if you connect to that port on each of the node, you will actually go to that services, and that service will actually point you to the port that it selects. Then finally, there is a load balancer type of service. Load balancer type of service creates a load balancer on the cloud, and using that load balancer service, you can actually connect to your service from the outside world. It's very popular for connecting your application to the outside world. Then there is two types of resource for configuration management. One is config map and one is secret. Both have key value pairs in their specification, so you can store data in key value pairs. So the main difference is you store confidential data like password, tokens, keys, etc. in secrets, and you store non-confidential data like your database configuration or your application configuration in the config map. So how do the pod consumes it? The pod can consume the config map or secrets in different form, like you can pass it via environment variable in the pod specification, or you can pass it via command line argument in the pod, or you can mount the config map or secrets as file in the pod. So the pod can actually use that file from your config map or secrets. So you can actually, these things are very important for managing database, because in config map, you can store database configuration. In secrets, you can store the database secrets, certificates, etc. Okay, now we will explore a bit more about the Kubernetes stateful set, because this is the main element to run databases on Kubernetes. So what is stateful set? Stateful set is the resource that manages stateful application. So what is a stateful application? A stateful application means that you have an application that have a state. So what does it mean? When the users connect to your application, the application keep tracks of their sessions or the transactions that's happening on the application, and it can react very differently from for same input given by the user based on the state or history that it has. So suppose a user is requesting information from the your application. It actually from its states returns the information, but when the user requests for the same information after some time, in the middle it can be changed by other user or by other means. So user is not guaranteed to get the same information because the state can change. So the stateful set is useful to manage the application that have a state. Then StatefulSet manages sticky identity for each pods. This is very useful because each pod is now uniquely identifiable. Then pods are created from same specification, same as deployment, but they are not actually interchangeable. You cannot interchange between the pods that the StatefulSet creates. Also, we have told earlier that each of them has a persistent identifier. So persistent identifier is important to have a stable DNS name. So if there are 3 ports, they will have 3 different names, and they will stay same until the life cycle of the stateful set. Then each port can have different volumes. So if you see the diagram here, this is a stateful set. It creates 3 different ports. Each of the ports has their own persistent volume. So each of the pod can keep their own data in their persistent volume. Also, the pod, we can call this pod 0, we can call this pod 1, and we can call this pod 2. And this identifier will always be same until the stateful set exists. So it is very important for running databases on Kubernetes. Then the features of a stateful set are we have already told about. It has a stable and unique network identifiers. So with the name that we have told, pod 0, pod 1, and pod 2, you can actually create a unique DNS for each of them. You will be able to connect to them, and the pod can actually communicate between each other using those DNS. And they have a stable and persistent storage. So we can see that they have persistent storage. If the pod gets deleted, the PVC doesn't actually get deleted. It actually stays. When the pods come back, it can actually claim the persistent volume it already had. So it has a stable and persistent storage. Also, it deploys the pod in a graceful and ordered manner. Also, it scales the pod in a graceful and ordered manner, because when the stateful set deploys, it first deploys the first pod. The other pods don't come up yet, because when the first pod is up and running, then the other pods comes up one by one. So it's very important to run database, because when we're running database, we want, if our database has 3 replicas, we want one of them to come up properly, then we want other ones to come up. Finally, when stateful sets is sending rolling updates to them, it also do it in ordered fashion. So it will send the updates to the first one, then second one, then third one. This is also important for running database. So running databases in Kubernetes is actually challenging, because Kubernetes is very popular these days. A lot of companies are using Kubernetes now, but they're mainly using it for running stateless application or microservices. But the data layer has so many challenges. The Kubernetes provides you with the primitives like stateful set to manage your database, but it still has a lot of challenge. So suppose you are running your application inside Kubernetes. This is your application, and you need a database solution for your application. So you have actually 3 options. First option is you can go to a cloud provider based solution. So what are the cloud provider based solution? Like AWS has RDS, GCP, and Azure also have their own managed database solution. You can actually use those database solutions and connect those database to your apps. That's one possible solution. And another solution is to use hosted database services like MongoDB Atlas. Similarly, Redis Cloud or Elasticsearch Cloud, all of them has a hosted database services. You can actually use those. They host their database in some cloud, and you can actually use those similarly as the cloud provider. So finally, the other option is to run your database inside your Kubernetes. So you run your application and run the database parallelly to your application in the Kubernetes cluster, and your Kubernetes cluster will your application will be able to run those databases directly and communicate it with your application directly. So you have these three options here. So now the question is, should you run database in Kubernetes? Is it really reasonable to run databases on Kubernetes? My opinion is it's very reasonable to run databases on Kubernetes. We know that Kubernetes is now very battle tested and widely accepted. Accepted by many companies. A lot of big companies now uses Kubernetes. So you can actually run databases on Kubernetes. In the last couple of years, Kubernetes has it's very become more practical to run databases on Kubernetes. So now the Kubernetes has a support for a stateful application via StatefulSets. You can run a StatefulSets application like database on Kubernetes. As we have discussed earlier, StatefulSets provides you with a pod that has a unique identifier. So you can actually have a stable DNS name for each of your replicas of your database. So when you form a cluster with the replicas and a stateful set, you can actually create a they need to communicate between each other. So when they want to communicate between each other, they need a stable DNS to communicate. So via stateful set, it's possible to communicate with each other because they have a DNS that is stable. Also, in databases, in the clustered databases, you need different kind of volumes for your different replica, because in the clustered architecture, you have a primary node and you have secondary node. All of them has their own kind of role. So they have some different types of data. So you need the persistent volume for each of them, and each of them has their own data. The stateful set allows you to do that. Also, there is the concept of custom resource definition, or CRD, which is now generally available. So you can use it is a very powerful tool, custom resource definition. You can actually create Kubernetes native solution. You can make the database Kubernetes native using the custom resource definition. Operators use the CRD to support different user requests to add in their database. So it's very important to have a solution like this. Then there is CSI driver support. CSI driver is also GA now. You can also it can also do volume expansion and volume snapshot. When running databases on Kubernetes, the first thing that comes to users' mind, that can they take backup, like can they take the volume snapshot? So now you can take volume snapshot. So it's very easy to take volume snapshot using the support of CSI driver. Also, when you are running databases on Kubernetes, you may have a lot of data, and as days passes, your data grows, and after some time, you will need to expand your volume. So Kubernetes also currently allows you to expand your volume. Even you can expand your volume even without disconnecting it from your application. So Kubernetes, that's called online volume expansion. And if that's not supported, you can always do offline volume expansion, where you have to disconnect your persistent volume for your prod, then do the expansion. So all of these are now supported by Kubernetes, so it's easy to manage the volumes. Also, about security, many people today want to TLS secure their databases. So that's also made easy by Cert Manager. Cert Manager is a tool that's a kind of standard for managing database, managing certificates on Kubernetes. So if you're using Cert Manager, you can easily manage your certificate on Kubernetes. You can easily make your database TLS secure. Also, I think the missing piece that the Kubernetes had is the to running database on Kubernetes is the operators. So now there are a lot of operators that are stable and running properly, and they are very mature. So when you are running database on Kubernetes, you actually have different kind of options like actions, like you have to provision your databases, and you have to give your database TLS certificates. You have to do kind of day two operations, like you have to update your versions. You have to change your configuration. You have to scale your resources. You have to scale your replicas, etc. There are many kind of actions you need to perform on a database. So operators actually make those easy to do, because those are nothing but a set of operations. When you are using an operator, the operator makes it easy to follow this operation, because in operator you can codify and automate the whole process. So for example, if you want to update the images of your, update the version of your database, you need to, sorry, you need to update the images of each of the ports. So like you can have 10 ports or 20 ports for your database if you are using a sharded version of your database. So if you try to do it manually, it's a very hard process, because you have to know which one is the primary of the of your cluster, which one is the secondary. You have to change the image of the secondary first, then do the primary. Then when all of them comes up, then you do the router, etc., etc. Then finally you check for if everything work properly, all of those things. So operator actually can make all of those things easier, because they can codify all of the procedure automatically. So with operator, it is very easy to manage databases on Kubernetes. Then there is a people actually need disaster recovery tools, like they need to back up and recover their database when some disaster happens. Now in the last couple of years, Kubernetes has a lot of disaster recovery tools. You can use those to actually back up your database and recover when a disaster happens. Also, we can see that the database vendors themselves are introducing their own database operator. I think they see the potential of using databases on Kubernetes, or I assume their users are demanding them to have a database for their operator. Uh, Nonetheless, it's we can see that database vendors are also introducing their own database operator. So you can actually run database on Kubernetes. It's very possible today to run database on Kubernetes stably and in a production grade way. So you are not alone while you are running database on Kubernetes. If you see some big names here like MongoDB, Redis, Percona, M3DB, Cassandra, etc., all of them here have their database operator or have a database Kubernetes native solution. So today, it's very uncommon to have a product and which doesn't have the Kubernetes native solution. Okay, so now the deciding factors. We have talked earlier about some three ways: the cloud providers, managed service, or database on Kubernetes. So you have three options when you are running your applications on Kubernetes. So what are the deciding factors? Which one you will choose? So these are the deciding factors I have come up with. So first is the choice of database. The database you want to choose, is it available on the solution you want to try? Then the access to different kind of services, like you want to use on-prem, or you want to use it on a air-gapped cluster, or you want to use it on cloud. So is the solution that you are trying there, is it have all those? Then the latency, will you have more latency or less latency if you use the solution? Then there's reliability. How reliable you used to use that solution? Is it mature enough? Or then if you're getting vendor locked, if you're using that service, then your data are you controlling your own data, or you are giving your control to them? Then there is performance. Can you access the SSD that has the maximum performance? Then the disaster recovery solution, are they available for your database? Then the pricing, is it expensive or is it cheap? Like, then operating complexity, is it complex to run the solution, or is it easier? Then the observability, can you observe your database with some observability? Can you monitor your database properly with the solution? Then customizability, like you want to use some plugins, or you want to use custom sizes, you want to use different kind of configurations. Can you do that? Then the third-party tools integration, can you use third-party tools with the solution? Like you want to use PostGIS or TimescaleDB for Postgres, etc. Then the ease of use, is it easy to use the solution? They're in a learning curve when you are using the solution. So we'll check all of these for each of our solution. So first, the cloud provider-based solution. So when we are talking about cloud provider-based solution, the choice of database is unlimited. There, you can actually choose for most of the databases, the cloud provider actually provides you a solution. So you have a good choice of databases. Then the database cloud providers are actually very reliable and they're mature enough. So that's also a good thing. Also, they are very easy to use. That's the main point of using a cloud provider based solution. You can actually click use one click to deploy a database. So they have the dashboards where you can click and deploy a database, and they have dashboards, so there is a great observability there. They provide you with a dashboard, so where you can watch what's happening on the database and etc. And there is no learning curve actually, because when you are using those, all of those things are you can see in the dashboard, so you know what to do, so there is no learning curve. You can easily use those. Then if we talk about operating complexity, there is no operation complexity. You can, if you want to back up your database, you can just click on the dashboard and you can back up your database. If you want to restore your database, you can just one click on restore. The database is restored. And the disaster recovery, they provide a good disaster recovery solutions, so like for backing up and recovery the database. So now the issues. The first issue is flexibility. So you cannot run your if you're running your database on prem, your application on prem, or in a air-gapped cluster, or you want to run on IoT devices. So that's not very flexible to use when you are running such thing. Even when you are using air-gapped cluster, you cannot even use cloud. So that's not a solution when you want these things. Also, when you want your data to be in a specific location you want, you cannot use the cloud provider solution. Also, the pricing. If you see the pricing of the cloud providers, if you see the underlying VM that the cloud provider using, for example, AWS RDS, if you go to their website and see the pricing of them, you see that the database pricing and the underlying VM pricing has a lot of difference. So they are charging you a lot for using the database services, but the price of the VM is much cheaper. So they are actually charging you a lot for the using their database services. Then there is latency. You are running your application inside Kubernetes, and the cloud provider based solution is actually outside of your Kubernetes. So there will be a lot of latency. Then there is you are not in control of your own data. You have to keep the data where the cloud providers want. Then the customizability. You cannot, in most of the cases, you cannot customize. You cannot use your own configuration. like you want to configure it very customizably like you want, or you want some you want some plugins to use with your database. You cannot use those in most of the cases, because they only provide you with some solution. You have to use those to deploy. They're very good and in what they provide, but you cannot customize it properly. Then like third-party tools integration, like with Postgres, you want PostGIS or Timescale DB, etc. So if you want to use those tools, most of the cases you won't be able to use those. Also, there is a possibility to be locked by the vendor. If you are using their databases, you have to use a lot of their services so that you can actually get the good performance from their database solution. Then there is the database vendor solution like MongoDB, Elasticsearch Cloud, Redis Cloud, etc. We have all of the problems that we have discussed before, like you don't have flexibility, the pricing is high, there's latency because it's running outside your Kubernetes. Then there you are not in control of your data. It's not really that customizable. The third-party integration is difficult. Then you are being vendor locked by those vendor. And there is another problem is choice of database. It can be possible that the database you want to use doesn't have a solution, vendor-based solution. So there is this problem also. And the good thing about the cloud-based solution also exist here, like they are reliable because they are like in MongoDB Atlas, you are using MongoDB and you are using the product from them. So they are very reliable and mature enough to handle their product. They are also they also provide a good observable solution. You will have a lot of dashboards there to monitor your database. They are really easy to use, and they don't have any learning curve. Also, operating complexity is pretty minimal. Also, they do provide good disaster recovery solutions. Okay, now we come to database inside Kubernetes cluster. Okay, so here the issues are Kubernetes is not that reliable because it's very new. But I would say in the last couple of years, Kubernetes has become very reliable. As I have talked earlier, it has now custom resource definition. It has stateful set. It has CSI drivers. All of them are GA now. So I think it has become more mature in the last couple of years. So you can use it reliably. Then the ease of use and learning curve. These are the main thing that very difficult for running database inside Kubernetes. If you are using an operator, you will have to learn their different kind of CRTs. You have to learn their different things, how to do this, how to do that. So you have to give some effort here. So the ease of use when you are starting your journey is very difficult. But when you get used to it, it becomes way a lot easier because you know everything. You just apply a YAML, then it actually happens in the cluster. Also, the learning curve is there is a learning curve, so you need a bit of time to get used to those. Also, the operating complexity is a bit higher. Like if you want to use a run database, you get download some stuff from the internet. You use a database container. You spin off a pod with that container, but you find a bug. Then you have to solve that bug. You go to the Slack channel. You ask the developer of that open source software to solve it for you. They solve it. You use it. So there is a lot of process when you are running this. But when you are using operator, this thing becomes easier because operator actually makes it easy to run those things. Like you want to use a version upgrade, so they make a procedure so that easy to do the version upgrade. And finally, disaster recovery. It also became pretty easy in the last couple of years, but it's still hard. I think it will become more easy in the upcoming days. So these are the issues that Kubernetes running Kubernetes on Kubernetes has, but I don't think there are some fundamental issues that that is blocking you from running databases on Kubernetes. If we check the what database on inside Kubernetes brings for you, the choice of database. So you don't have to worry about the choice of database. You have a lot of options. If your database has a containerized solution like a container or Docker container, you can use those database inside Kubernetes because when you are choosing the database, you just need to run this in your cluster with the image. So if you have the database image, you can run that on your database. Then the flexibility, it has a lot of flexibility. You can run on-prem, you can run on AirGate cluster with some private registry, you can run on IoT devices. So the flexibility is great here. Also, if we talk about pricing compared to the other solution, the pricing is a bit less than others. So it's also a good thing. You will get a good performance here. The latency here is very less because you are running your application and your database in the same VPC, so they don't have any extra latency. Then you are on control of your own data. You want to store your data in some local NVMe or SSD, you can do that. Of course, you have to pay the price for the hardware, but you can do that. You want a lot of performance, you can do that with your own local SSD, or if you want, you can use the cloud SSD also. Also, observability. Now Kubernetes has Prometheus, Grafana. Those are pretty much standard. You can use Prometheus or Grafana to observe your database. They give you a pretty good observability. You get some dashboards. You can observe your database actions, what's happening on the database pretty easily. Also, customizability. You can customize your database uh, anything you want. Like you want to use custom plugin, you want to use custom size, you want to use configuration, you can do all of that because the possibility is limitless there. You are in control of everything, so you can do everything here. Also, third-party integration, you can use PostGIS, you can use timescale DB, anything you want, because you have a Docker container, you can install those third-party tools and use those because you have everything here when you're running. You can use another container to do that. You can do that also. Also, you are not actually vendor locked in here because there are a lot of tools or open source tools. You can use any of those. So now I assume I have convinced you enough that you can run reliably database on Kubernetes. So now the question is what you should use. You have two solutions, like you can use Helm or YML based approach. You can just use a Helm chart to do that, or you can use operators. So let's see them side by side here. So when you are running databases with Helm, it's pretty easy. There is no additional tools required because you are just doing a Helm install command. It deploys the database nice and easy. You don't need anything else, and you don't need any understanding of there is nothing to understand here. You just know the Helm, you just install the Helm command, then your database is up and running. There's nothing. But for operator, you need to install the operator first. You need to understand different operator specific custom resources before running the database. So that's actually you need to understand those. But with Helm, those are easy. So with Helm, the deployment of your database is very easy. But the problem is it only deploys the database. It's not aware of the database lifecycle, what's happening on the database, what is the status of the database, what is the current health of the database. Many things you cannot do with the Helm. But a operator, it's actually specialized to run databases. So it's aware of your database. It aware of the complete life cycle of the database. It knows what's happening on the database, so it can show you different things about the database. Also, there is no self-healing for when you are running database on here. You are in charge of everything. You are in charge of fixing anything that happens on the database. Like a pod goes down, it doesn't counts back properly, then your cluster now has one or two pods only if it had three pods before. So it's not working properly anymore. When it comes back, you can see that a split brain situation happened. There is now two primary. So you cannot actually use the database. You have to fix it manually going inside the database. But for operators, some operators are smart enough to fix some common problems. So on operator, it doesn't really happen the split brain problem, because the operator knows that when a port comes up, there were previously another primary, so it wants to join the pod in the database, so it can do all those things. Then there is the day two operations, like backing up the database, restoring the database when disaster happens, scaling horizontally, scaling vertically, upgrading the database to a new version. Also, you want to use a new configuration. You want to reconfigure your TLS setting. There is a lot of operations that has in your database. So some operators can actually handle the two operations too. So those database can back up or restore your database. They have a solution for scaling. They have solution for upgrading, etc. So you can do all those with operators. So I think you are convinced that operators are the best way to run database on Kubernetes. Now we'll go on a hands-on demo. Please follow this link. I'm sharing this on Zoom chat. We'll follow this to give you a hands-on demo. You can also follow this to run database. I'm sharing it on the Zoom chat. I see a question on the Zoom chat. Can we run DB replicas of a stateful set in parallel instead of sequential? I think it's not recommended to run in parallel instead of sequential, because when you are running database replicas, when the ports come up, you first need the primary to come up. If you run sequentially, you have all the ports. So when all the ports comes up, all of them can make themselves primary. So it's not practical to run the sequentially. So you when you run in order in a stateful set, the first port comes up and it becomes primary. Then another port comes up, it joins to that primary, and another port comes up, it joins to the cluster again, becomes secondary. So now you have a proper solution where you have a replica, primary, secondary. So I have a proper architecture with the stateful set. So it's not recommended to run sequence. So now we'll deploy, we'll run database on Kubernetes. So first you will need a kind or minikube cluster. You can use this instruction to install kind, and you need to have a working Helm installation. If you don't have it, you can install Helm from here. Also, you need to clone this repository, and you have to make this your current directory so that we can run all the commands that I have described here. So please download them or clone this repo. We can start creating the kind cluster. Let me bring up a terminal and run the command kind create cluster. It will take some time to create the cluster if you don't have the images installed on your Docker. I already have this, so I have the kind cluster up and running. Okay, so what is kind? Kind is a tool that helps you to run Kubernetes in your PC. So we are using that. If you have a working cluster, you can use that. You can use Minikube if you want. This is the installation of kind. We are just using kind here. You don't have to use kind. You can use any Kubernetes solution you want. So if you have your kind cluster created, we will start installing supporting tools. First, we will need to install kubedb. To install kubedb, you will need a trial license first. You can go here and give your name, email, and you can use your personal email too. And the product is kubedb Enterprise. You have to provide the Kubernetes cluster ID. You can find the cluster ID using this command. If you provide this command in your terminal, you'll see that it provides you with the ID. So you can provide this ID here, and if you agree and submit, the license will be mailed to your license will be mailed in your email. Please download the license and save it as license.txt under the folder same directory, this directory. Then you will be able to install the command that we are providing here. So let's do that. Okay, Avinash said that kind is a tool for running local Kubernetes cluster using Docker container nodes. Yes, that's true. It uses Docker container to run your databases in your PC. Okay, I got the license. Sorry if I go to here. Okay, as you can see, I am in the workshop Git repository, and here we have all the data. And here you can see that I have a license.txt that I have downloaded from the Tips website. I got a email with the license, and I saved it here using the name license.txt. You can use different name also, that doesn't matter, but then you will have to change when you run the helm command. You have to change the name here. You have to provide a name that you have provided. Okay, I think everyone has done these parts. Let's add the helm repository. I already have added this. You can add this apps code helm repository, then run helm repo update to update your repository. Then you can search for this kubedb repository. If we do this, you can see some results if you have done the previous steps successfully. So we can see that the apps code kubedb has the version 10.042. 2023, we will use that to install our database, sorry, operator. So we are going to run this helm command. So here you can see that we are running the helm command where we are probably enabling different kind of operator. We'll talk about them after a little bit. Also, we are providing the license that we have got from the email. We can now watch the ports to see if our database is running properly or not. As we can see here, we can see some operators are being installed here. The first one is running, then this one. So we can see that there are multiple containers, multiple pods here. We'll talk about them after a little bit. Let's install the second one. We'll install Stash. Stash is a tool for backing up and recover. It also a product by Upscot. We search the repository, we'll see that it has a version 2003. We'll install that version. Let's install that. Okay, we'll let it install. Here we can see that there are some operator that got installed when we installed the kubedb helm chart. So you can see that here is one operator called autoscaler. It actually manages the auto scaling for your databases. Then there is dashboard that manages dashboards. Then there is ops manager, which actually manages the day-to operations. Then there is the provisioner operator, which provisions your databases. Then there is schema manager that manages your schema of the database. Then finally the webhook server that manages the Kubernetes webhook for the kubedb database. I think our Stash is already installed. If you see here, there is a new port called Stash Enterprise. So our Stash is already installed and up and running. So let's go to the next step. We'll use Panopticon. Panopticon is a tool by Upscot, which makes it easy to get metrics from your YAML. We'll see that later. Let's just install it. Search that we have a new version here. Let's install that version. Okay, we are using Panopticon. We should see a new pod here. If you see here, you can see that there is a new pod Panopticon. So our Panopticon is installed. Now we will install some kubedb metrics. With the help of kubedb metrics, we will be able to see the database dashboards, etc. It also has a version. Let's install this. So it doesn't have any port. It actually installs some resources. So you won't see any port here. Now we will install Prometheus. Prometheus, I have talked about Prometheus earlier. It's the monitoring tools that is standard for Kubernetes now. We will install the Prometheus. You have to run the Helm repo at Prometheus community, then run Helm repo update. Then you will be able to install the latest version of Prometheus using Helm. Let's install the Prometheus. We'll be able to see a lot of ports coming up here. After installing Prometheus, we will need a last tool called Cert Manager. I have talked about Cert Manager earlier. Cert Manager is a tool that manages certificates for you. We will deploy database with TLS security, so we'll need to manage certificate. You will be able to see the certificates and manage the certificates if we install the cert manager. So let's wait for the Prometheus. Okay, we can see that our Prometheus ports are up and running under the monitoring namespace. So okay, Prometheus is installed. Now let's install the cert manager. Let's search for the cert manager first. We can see that there is a new version. Let's install that. It will bring up some port. We can see that some cert manager ports are coming up in the cert manager namespaces. So we can see that our cert manager is also deployed successfully. So if you have completed till now, we are good to go to our next session. You can follow these steps to run all the tools. So now we'll start with chapter 1. So we'll deploy MongoDB database. As we are deploying MongoDB database, I should give you a brief introduction about MongoDB, because we'll talk a lot about MongoDB in the whole workshop. So I'll let you guys install all of the tools in the meantime, because it can take a bit of time to install all of the tools. In the meantime, I'm going to talk about MongoDB. I'll give you a brief introduction of MongoDB. So what is MongoDB? MongoDB is an open source database, which is actually a NoSQL database. It's not a SQL-based database like Postgres or MySQL, where you have a table, you have rows, you have columns. But in the NoSQL database, you doesn't have anything like that. You have something called document. You have a JSON-like data structure. You put your data in that JSON-like format. You have a dynamic schema. In the SQL-based approach. You don't have you have a specified schema. That means you have a table that it has to be 3 columns, 4 columns. That's already defined. But with the NoSQL database, there is no actually defined structure. You can create it anywhere, anyhow you want. You can have 5 data for your first document. You can have 2 data for your second document, etc. So there is no defined schema. You can use a dynamic schema. Also, it's a non-relational database. Oh, non-relational means the database tables, we know that the tables have some relation between them. So in this case, the document doesn't have any relation with other documents. In the SQL databases, we have primary key, second, foreign key, etc., to make relation between 2 tables, etc. But here we don't have anything like that. And also MongoDB supports the replication and sharding. So you can create multiple replicas for your database. Also, you can manage sharding. We will see those things later. So if we compare the terms of relational database with MongoDB, we can see that relational database has something called database. Inside the database, you have many tables. MongoDB also has a thing called database, and database has tables. The tables, the equivalent of table here is collection. We call it collection here, and it has rows. Table has rows, but collection has document, which are actually JSON or BSON format. BSON is something like JSON, which is actually think of MongoDB. Then there is column, which is called field here in MongoDB. Then there is partition in database, relational database, which is shard here in MongoDB. And if you join in your relational database, that means embedded document in MongoDB. So if we see the relation between relational database and MongoDB, we can see that this is a table, right? So there is student ID, student name, age, college, etc. columns here, and some rows. So you can see that if we want to convert this table into a collection. This is a collection. Each row becomes a document. So this is a document. This represents these rows. This is a document. This represents these rows. This is a document. This represents this row. We can see that each of the document has their ID, student name, age, college, same as this relational database table. And as a whole, it is called collection here, where it is called table here. Then these are some basic commands of MongoDB. You can run show dbs command to list all the databases. You can run db command to show the current database. You can use dbname command to switch to a database, or if the database doesn't exist, you can actually create the database. Then there is show collections. It will list all collections in the database. And if you want to insert document in a collection, you just put db.collection name dot insert to the document. If you want to show all the documents in a collection, you just have to use db.collection.find. It will return all the collections in the document. Sorry, all the documents in the collection. Then if you want to search for a data, you can use the find command to find a specific data. So that's all the basic command for MongoDB. We will see all those when we deploy our database. So now the MongoDB architecture. There are three kinds of MongoDB architecture. One is standalone server, one is replica set, one is sharded cluster. So the standalone server is nothing but which has only one server. A replica set has multiple servers, so the data can replicate on each other. And there is shard, which also has multiple servers, but the data is distributed on each of the shard nodes. So these are the three setups for MongoDB. First, let's talk about standalone. Standalone only has one MongoDB process that actually maintains your data. So there is no redundancy of data. So if you lose this server, you actually lose all your data. So there is no fault tolerance against loss of the database server. So if you lose the one database server that you have, you lose all your data. If the database server also comes back when it doesn't exist, user won't be able to use your database. So it's not actually recommended for production use. You can use it for your toy setup or hobby project, but it's not recommended for production use. Then there is the thing called replica set. Replica set is a group of MongoDB process that maintains the same data. So there are like multiple replica of your database, and each of the replica maintains the same data. Then there are multiple copies of the data in different servers. So you have to put all the different replicas in different servers. So even if one server goes down, you can always get your data from the other servers, and the database actually keeps functioning when you have lose one server. So it provides you with redundancy. So you have redundant data, and this increases the data availability. So as you have multiple copies of your data, you have the more availability of your data. It provides a level of fault tolerance in the loss of database server, because if you have 3 replicas in your database, if you lose one replica, you all still have 2 replicas left. You can still connect to the database. You can still run operations on the database on that time, because you still have the data. So it provides you with a level of fault tolerance, and it contains several data bearing node, and it can contain non-data bearing node like arbiter too. The main members of the replica set are primary and secondary member, and it has some optional members like hidden node, arbiter nodes, etc. So if you see the primary member of the replica set, it actually receives the write operation and also the read operations by default. So when the client application, when the client applies some query or write operation, MongoDB applies the write operations in the primary node of the replica set. And the primary actually records the operation, which is called oplog. It records the operation in the oplog. Secondary member sees the oplog and actually replicates the oplog and applies those oplog. So it maintains the same data as the primary. So there is only one primary per replica set. You cannot have multiple primary. Then you will have a split brain situation if you have multiple primary. So there is a simple architecture. Here is a primary member and two secondary member, and your client application is writing and reading here on the primary, and the secondary members are replicating the data that are in the primary node of your primary node, and they are replicating the data, though all of them have the same data. Also, they have some different data too, like it's primary, so it has to maintain the state primary. It has secondary, so they have to maintain the state that they are secondary. They have some different data too. That mostly the data that clients is going to use, the client data, the client document that they're creating, that are similar in all of the replicas. Now the secondary member never receives write operation from client. It receives the write operation from the primary directly. The user writes the operations on the primary member. Then the primary then the primary member is replicating the secondary member is replicating those data. They're receiving the write operation directly from the primary, but the client is only writing or reading from the primary, and the secondary is receiving them from the primary. It can accept read operation from the client. By default, in MongoDB, you only receive write and read operation on primary. But if the client wants, they can issue the command on secondary and receive data from secondary. They can do that too. But they can never write on secondary. They maintain copies of the secondary data that we have talked earlier. Replica set can have one or more secondary. It can have multiple secondaries. Secondaries can also become primary member. When the current primary is gone or it's unavailable for some time, the secondary member can become the new primary. Where if the current primary is unavailable, election occurs. So where the winner of the election becomes the new primary. So this is the election scenario of the database replica set. So for some reason, the primary got lost. We can see from our previous diagram that the secondary member primary all send heartbeats to each other. That means they prove that they are currently available. So I am available, it sends a heartbeat to the secondary sends a heartbeat to the primary. So all of them communicate with each other to send a heartbeat. So for some reason, the secondary members miss the heartbeat from the primary. So that means that if both of them misses the heartbeat from primary, that means the primary member is not available anymore. So then they decide to held the election. Then they held an election and choose a new primary. And the new primary becomes the client data now comes to this primary member, and replication occurs from this to this secondary, and heartbeat also occurs here. So even if the previous primary comes back, it will join this cluster as a new secondary, and it will replicate the data from this new primary. So it will work like this. So you will always your data is always available here. So now the next thing is sharded cluster. Sharding is a method for distributing your data in multiple servers. Where you have a large amount of data. When one machine cannot handle all the data, you can use sharding. Suppose you have 100 terabyte of data, you can actually split it and make it 10 terabyte of 10 servers and store them in 10 servers with 10 TB of data. So as a whole, you have 100 terabyte of data, and sharding makes it possible to use those 100 terabyte data as a whole, even if they are on different servers. It also allows you to scale horizontally. Horizontal scaling means you can add new machines to distribute your load or distribute your data. So you currently you have 10 servers. You can add 5 more to distribute your load or distribute your data to the new servers. Benefit of sharding is it increases the read and write throughput, because you can, as you have multiple shards, you can actually read and write write on both of the shards simultaneously. So your read and write throughput becomes more. You can run more read and write operations parallelly. And you have increased storage capacity, as I told earlier. You have 10 terabyte of capacity on each server. If you have 10 server, you have total of 100 terabyte of capacity. Then data locality, you can put your data in different zone, and different zones user can use that specific shard to access their data. So you can use the shard as local data. Then sharded cluster has cluster has 3 components: shard, config server, and mongoose. Let's see those. So the shard is a replica set cluster, similar to config server. That's also a replica set cluster. The shard consists of subset of data. So you have 3 shards. That means your data is distributed in 3 shards. If you have 5 shards, your data is distributed in 5 shards. So you have like 100 data, you have 5 shards, you have 20 data on per shards. So you can distribute your data on the shards. Together all the shard, you have entire data for the cluster. If you perform query on a single shard, you will get only get the subset of data. Like you have like 100 documents and you have 5 shards. Each shard contains 20 documents per shard. So if you go to one shard and perform a query, you will only get the data that shard has. You will not get the other 80 data. So to get all the data, shard actually has mongoose, a router. You only connect to the mongoose, and mongoose decides for you which shard has your data. Then there is config server, which is also a replica set, and that manages the configuration and metadata settings for your cluster. It includes ranges of data on every shard. Also is used for maintaining distributed blocks. And we have talked about mongoose. It's not a replica set. You can have one mongoose or more mongoose depending on the load on the database. They can work parallelly to serve you read and write operation. The mongoose actually routes your query and write operation to the shards. So application connects with the mongoose directly. It doesn't connect with the shards. Application never connects directly to the shards, and mongoose doesn't actually have a persistent state. So if we see the architecture here, we have 2 mongoose. So we can have more mongoose too if we want, and we have 2 shards here. We can have more shards. So this shard is a replica set, this shard is a replica set, and there is config server. This also replica set. So if you want, you can keep your shards like 3 replica. So each of the shard now has data replication. So you have distributed your data. Also, you have replicated your data. So for disaster solution, it also works great, but it's not very cost effective because you will need a lot of servers for running. Like here, you need to If you're running 3 here, 3 here, 3 here, you have like 11 ports or nodes. But it's very important for running a database, so where you need a lot of data, where you have a lot of read and write query. So the application never directly writes to the shard or reads from the shard. Application only connects to the router called Mongoose. It issues the read and write operations here. The router actually finds the actual data that it requires. For example, if this data wants data from this read write wants data from collection 1, the router actually calculates those and sends the request or routes the request to both of the shard, as the collection 1 exists in both of the shard, as you can see here. So it sends request to both of the shard. Also, when you request another user or the same user request read and write operation on collection 2, it only exists in shard A, not in shard B. So the router knows that, and it sends the routes the query to shard A. So how does the router knows this? We actually know that the config server includes the metadata and configuration for the cluster. It actually holds where it actually knows where each shared data remains. So Mongoose actually connects to the config server and writes those. Mongoose actually maintains a cached copy of the data too, so that it can read write data more efficiently. Okay, that's all for the basics. Let's get back to our demo. I hope that everyone already I hope that everyone already installed all the supporting tools. Let's create our database. First, we'll need a demo namespace. Let's create the demo namespace. So we have created the demo namespace. Now, as we are going to deploy a TLS secured cluster, TLS secured database or cluster, we will need a CA certificate and CA key. If you see here in the left side, you can see that there is a CSR and CA key. Those are just dummy CSR and CA key. We'll use this CA certificate and CA key to issue our certificates for the database. So let's create the secret with this CA certificate and CA key. You can see that we are providing the path of the CA certificate and CA key here. Let's apply this. Make sure that you are on the directory of the workshop, this Git repository, so that you can run all the command. We have provided some relative paths here. So you can just copy and paste this to run the command, all the commands here. Then we'll need a issuer. So what is the issuer? Let's see the YML of the issuer. If you check the YML of the issuer, we have talked about cert manager before. The cert manager has a CRD called issuer. This issuer is actually responsible for issuing certificate for us. So here in the specification, we are providing that we have a CA. We are providing the secret name, CA name here. So when okay, in the chat we say that someone is requesting the GitHub link. Let me provide that. Okay. Okay, so we are using a issuer. The issuer, actually what issuer does, it sees that it has a CA in this secret. It will sign all the certificates issued by this issuer using this CA. So it will sign sign all the things, all our certificates. We'll be able to use them efficiently in our database. So let's apply the issuer. let's check the issuer. We can see that our issuer is ready to, so it's ready to use. Now let's we will use two configuration for our database. Let's check those. So first configuration is mongod.conf. It has a simple configuration like max incoming connection as 50,000. And then there is another configuration called replica set.json, where we are providing the election timeout millisecond as 50,000, 5,000. The default value for this is 10,000. We are making it 5,000 so that we can see that we are able to change the values. So we have these two configuration. You can see that in the folder. Let's create a secret using both of the configuration file. So I've created a custom config secret with both of the mongod.conf and replica set.json. Now we will create another config map with the init script. So what the init script do is when the database is spinning up, it will run this file only once. So we are in the when you are running a database, sometimes you may need to run some initial script to make your things work. Like you have to put some initial data in your database. You can do this with this init script. So here we are just providing a simple script. So we are getting a database called kubecon. In the kubecon, we have a collection called workshop. We are inserting a sample document in the workshop so that we can see that our unit script is working perfectly. So let's apply that unit script. Our unit script is applied and created. Now let's apply the MongoDB YAML that we have. Let's apply it and then we'll check out what's inside the YAML because it will take some time to get it ready. We have applied the YAML. We can watch what's happening in different terminals. Let's watch the MongoDB. Let's watch the pod that it's creating. Okay, let's see what is inside that YAML. Okay, we can see that in the YAML, it's a kubedb specific YAML. The kind is MongoDB, so it's a custom resource. In the metadata section, we are providing a name and namespace for our database. In the version section, we are providing that we want a 4.4.6 database. And we want TLS enable for our database. So we are providing a SSL mode. And in the TLS setting, we are providing the issuer name that we have just created. And in the certificate section, we are providing a dummy email address so that we can configure it as you want. We are just providing it to show that it works. Also, we are providing the cluster authentication mode as X509. That means it is specific to MongoDB. It means you can actually connect to the database without user and password or just by using a certificate. Okay, then we are providing the name of our replica set. We are just simply putting the name replica set. We want 3 replicas for your database. So we are providing replica 3 here. And in the pod template section, we are providing that we want the CPU request and memory request to be 100 millicore and the memory to be 512 millicore. All of this will be replicated to the 3 of the replicas. So all of our replica will have this CPU, this memory. Finally, we are setting some unit script that we have created as the config map. We can see that in the unit script field. In the config secret section, we are providing the config secret. Also in the storage section, we are telling that we want 1 GB of storage. So all of our 3 replica, each of them will have 1 GB of storage. And finally, we want to monitor our database with Prometheus. So we are setting some Prometheus specific information here. And here is a thing called termination policy. We're putting it as do not terminate. It means that we don't want to accidentally delete our database. So if you somehow accidentally run the delete command for your database, our web server will actually deny that request and you won't be able to delete the database as you have put do not terminate. It's like the safety feature you see on the cloud. When you want to delete something, they want you to confirm saying yes or the name of the database. So we can also, we have put a safety feature here also, because the database is a critical thing for your application. If you lose it accidentally, that's not good for your application. So we have put do not terminate. So if you really want to delete the database, you have to modify this value as other values, like we have delete or wipe out. You can set those values and you will be able to delete your database. Now let's see what's happening to our database. As we can see now, our all of the replicas, we wanted 3 replicas for our pod, as you can see here. We wanted 3 replicas for our database. As we can see, there are now 3 pods in our database. And the first pod is primarily, we are showing the role of our data. So the first pod is primary and other pods are standby. The role is actually a label. We have this is actually we actually put this via the operator. So if you check the MongoDB YAML, you will see that there is a label called kubedb role, which is the primary. I am just showing this with this field so that we can easily see which one is primary and which one is standby or secondary. We'll be able to see them change when we'll run some operations here. So if we check the get output of the MongoDB, we can see that the database status is showing ready. So our database is ready to use. It has different kind of phase or status, like this provisioning. So first we have seen the provisioning phase. That means that it is currently provisioning. We won't be able to use the database. Then there is data restoring phase, where the database is currently restoring from some data. The database is still usable in that state. And currently we are seeing that our database is ready. That means that our database is accepting connection ready. All the replicas are ready. You can use the database. Then there is another phase called critical. Critical means clients can connect to the database, runs operation, etc. But one or more replicas are not ready. For some reason, the one of the pod got deleted, or one of the pod is not working properly. Then we show the database phase as critical, but it doesn't mean that you cannot use your database. We are just warning you that something happened to your database. So with this phase, you can actually monitor your database. This is the very basic version of monitoring your database. You can see the status and you know that what's happening on your database. You can still use your database on this phase. Then there is not ready phase. That means you cannot connect to the database, you cannot ping to the database, you cannot write to the database. So we show that not ready. So if you see a not ready phase, that means you cannot use your database. Then there is a halted phase. Sometimes you may want, like you are doing a hobby project, but you want to keep all your data, but you want to stop your database in the weekend. So you can actually halt your database. By halting your database, all of the pod will be deleted, but the PBCs will still exist, so your data still exists. When you resume the database from halt, all of your pod comes back and claims those PBC, and you can use your things as is. So you can actually save save up your resources when you are not using, but you can still have your data by halting your database. Then there is an unknown phase when the operator doesn't know what's happening to the database. That we don't know actually if the database is usable or not. You can use it or not, but we don't know that. So these are the phase that kubedb supports. So now let's go to our next section. So now that our database is ready, we can connect to the primary member of the replica set. As you can see, we are executing into the first port, which is our current primary. We are creating a bash shell here. We are connected to our exec into our primary. So here you can see that it's showing the name of the port. Let's run some command to verify. First, we will connect to our MongoDB shell. As you can see here, we are providing our password, we are providing our username, we're providing TLS certificate key, TLS, and our client PM file. All of these are stored in the database so that you can connect to the database using those. So if we apply this, we are connected to the shell of the primary. So we are successfully connected. If we check the databases, we run show dbs command, you can see that there is a kubecon database. We know that via the init.js script, we have created a kubecon database, and there is a workshop collection and there is a document. Let's see that it has those collection. First, let's switch our database to kubecon. Okay, now let's check the collection. If it has the workshop collections, we can see that it has the workshop collection. Let's check out the data and documents in the workshop collection. We can see that the data we have provided inserted via the init script is exist here. So our init script worked perfectly. So now next we will check the config secret we have provided, the mongodb.conf. So we have provided the max incoming connection as 50,000. So let's check that out. We have to run the command called db.admin command. I have put all the commands in the GitHub repo. You can just copy and paste it. As you can see in the net incoming maximum connection is 50,000, as we have provided via the config secret. Also, if we want to check the data of the replica set JSON, we wanted to change the election millis as 5,000. I already said that the default value is 10,000. Let's see that. As you can see, the election time and millis as 5,000. So we have successfully did that too using the replica set.json. Okay, now let's check the replica set status. We know that we have 3 replicas. One of them is primary and 2 of them are standby or secondary. Let's check this out from our replica set status. You can see that there is a members field. We have first one, the ID0 port is the primary. Then the second one, the ID1 port, which is secondary. Then the third one, the number 2 port, which is also secondary. So it matches with the configuration we have provided. So it worked perfectly. Now let's see if we can insert some document manually. We are on the kubecon database. Now let's insert some data. Let's say a database collection, then insert some data called db1, maybe MongoDB. We have inserted one data. Let's insert some more data. Let's insert another called realistic search. or anything you want. Let's check if we have inserted them successfully. If we check the database collection, we can see that we have 3 documents here. So we have successfully inserted documents in our collection. Next, we will check out the Prometheus of our Prometheus graph or Grafana graph in our database. So to do that, first you have to port forward the Grafana service. Let's exit from here. So you have port forwarded the Grafana. You have to keep it port forwarded, otherwise you won't be able to connect. So you just keep it on another terminal, and we can go to this link. So we can see that we need a username and password. I have provided the default username and password here, but if you want to see it for yourself, you can actually see it from this secret. If you run this command, you will be able to see the passwords and username. You can see the password is prom operator and the admin user is admin. So let's use those and log in. So as you can see, we are currently connected to the Grafana dashboard, but as you can see, there is no dashboard to view. So we'll create some MongoDB dashboard using this repository. If you go to this repository, you will see that there are 3 dashboard JSON. If you open those up, you can copy those from here or just select all and copy. Then you can import them from here in the Grafana dashboard import. The instruction is also given on the GitHub repository, and you can paste it here and click load, import, and your chart is imported. And now let's import another chart, which is this one. We have imported this too. Then our final chart is this chart. So we have successfully imported 3 of our dashboards. Let's check one by one. First, let's check the MongoDB summary dashboard. If you check the summary dashboard, you will see that it's showing the status ready. And the database uptime is 15 minutes. If we check from here, we can also see that our database age is 15 minutes. So it's perfectly showing all the data. Our total CPU limit, total memory limit used by the database, total storage request. As we know that we have provided 1 GB for each replica, we can see that there is 3 GB. Also, we have provided the termination policy as do not terminate, which is also replicated here. Our database version, CPU uses, memory uses, etc. Okay, so disk uses, IOPS, throughput, etc. You can see all the information from here. Okay. Then there is another dashboard called MongoDB pod. If you go here, you will see the pod specific information. Like this pod has 14 minutes of uptime, and the QPS, latency, connection, cursor, etc. information. If you want to see the other pod information, like this pod has 13.8 minutes of lifetime. This pod has 13-minute lifetime with different kind of options. Finally, we have another called replica set. It is only for replica set cluster. So if you check that, it's showing that this specific pod is the primary of the replica set. The replicas are 3 members. The last selection happened 14 minutes ago. There is no replication lag. Also there are other kind of upload operation you can see from here. If we check another pod, you can see that it's the secondary. It doesn't have any election information because only the primary has the election information. Also the other things. So you can monitor your database very easily from these dashboards. Okay, so now let's go to the next section. We'll try to delete our database. Now let's try to delete it. We have told earlier that it won't be deleted because we have put a failsafe there. Okay, so as you can see, it's not being deleted. It's returning an error. Your webhook is denied this request, cannot be terminated. You have to change the termination policy. Okay, so we really want to delete the database. So let's patch our wipeout with termination policy as wipeout. Wipeout means it will wipe out everything. So now if we run the delete command, you will see that our database is being deleted. All of the pod will be terminated. Our database is there no more and there is no more pods. So our database is deleted successfully. Now we'll deploy a sharded cluster similar to the replica set cluster. But here we want to just put configuration for only the shard. And we will show that it's replicated only to the shard, not to the config server, not to the Mongoose. So just let's create mongodb.conf. It's a similar mongodb.conf as before. If we check that out, we are just putting max incoming connection as 50,000. We've created the secret. Now we'll apply the YML and I'll explain the YML while it's applying. As you can see, the status is provisioning. The version is 4.4.6. We should see some pod here. Okay, the first pod is coming up. Now let's see the contents of the YML. So it's a similar YML MongoDB. Also, we're providing MGSH, means MongoDB shard, and it's in the namespace demo. Similarly as before, we are providing a version. Also here we are providing that we want 3 replicas for our config server. In the shard topology section, we are providing config server, Mongoose, and shard information. We want to 1 GB this request and limits for our config server. Also want 1 GB storage for the config server. All of the replicas of the config server. So all 3 will have 1 GB of storage. And there is 1 Mongoose replica. So all of the Mongoose will have this request and memory. And in the shard section, we are providing that there are 3 replicas and 1 shards. And we are also providing 1 GB of storage. So there are the total of 3 shard members. So all of them will have 1 GB of data volume. And then we are providing the limits and CPU here. Finally, we are providing termination policy as wipeout, as we want to delete it immediately. So all of these things will be replicated to the pod. Let's see. If we check here, it's still provisioning. We can see that the config server ports are all come up. We wanted 3 replicas for our config server, as you can see here. We can also see that there are 3 members of our config server. Also, we wanted 1 shard with 3 replicas. We have 1 shard. We only have shard 0. If we wanted 2 shard, we would see that there is some ports with prefix shard 2. So we have got 3 replicas for our shard replica set. Then finally, we have 1 Mongoose replica. You can see that Mongoose doesn't have any storage, because we have said earlier Mongoose doesn't keep its state, so we don't need any storage for that. It can just write on memory and use from cache. So we can see that all of them of the pod are ready and running. Also, we can see the database status as ready. So we are all good to go. Now let's verify something from the inside the database. So we are now connected to the Mongoose. As you can see, we are connecting to the executing to the Mongoose and connect to its bash. Now let's run MongoDB command. As you can see, we haven't enabled TLS for this cluster, so we are not providing any TLS here. We are connected to the Mongoose. If we run the shard status, we'll be able to see the shard status. So we can see the shard versions, the number of shards, which is 1, and the shard members as host. We can see here the ID of the shard is shard 0. We have 1 active Mongoose, and we have balancer enabled. We have some other database information, the data is partitioned or not, database is sharded or not, that kind of information. Now we will try inserting some data. As you can see, there is no data. We haven't provided any unity script here. So you will see that there is no database called kubedb here. So let's create that. We have created a database called kubecon. Now let's insert some data in the database collection. Same as before with that we have done for the replica set. There is no other special things. We've inserted 1. Let's insert some more. Let's insert 1 last. Let's verify that. As you can see, all of the data are inserted successfully. So as we have only 1 shard, all of the data will go into this shard. But if we had sharded this data and we had 2 shard or 3 shard, all of the data would have been distributed in different shards. Now, if we check the shard status, we'll be able to see in the database section, there is another entry called kubecon, the primary shard for this shard 0. And it's not partition, means it's not sharded because we haven't issued the command to shard it. Also, there is no point of sharding it because our database is not actually doesn't have more than 1 shard. Okay, now let's exit from here. Now let's connect to one of the shard to see the data there. We are connected. Let's connect to the database. If we check the show DBs, you can see that the kubecon database is here. If we check the data, we can actually run the commands here. We can actually get all the data here. But the problem is we only have 1 shard. If we had multiple shards, if we run this command, we would see on the subset of the data. It could be we can see 2 data here and 1 data in another shard. Because of time limitation, we didn't create a with 2 shards because it takes time to bring up the with 2 shards. You can try it yourself if you want, but you will have to shard this database first. Okay, then we can say that we have provided mongodb.conf as we have talked earlier in the shard, so it should have this information. If we run this, we can just copy the command. Here is the command. Oh, we can see that here the max incoming connection is 50,000. So our configuration is successfully propagated here. If you also run the replica set status, as it is a replica set, it should return the data. Sorry, I made a mistake. Status. Okay, as you can see, there is one replica, two replica, and three replica as we have provided in our configuration, and this one is primary and other ones are secondary. So it's a perfect replica set. Let's exit from here and let's exec into one of the config server to see the data there. So we are connected to the config server primary. If we try to check the database, so the database doesn't contain the KubeCon database because the KubeCon database is only hold in the shard. The config server is only for the maintaining metadata. It's not for keeping user data. So we don't see the KubeCon database here. If we run the RS status, we will be able to see the replica status. It has 1, 2, and 3 replica as before. So as we provided in our specification, and there is one primary and 2 secondary here. So it's a perfect replica set too. If we also check this command, like if we try to find if we check the net section, we don't see the max incoming connection at 50,000 because it's not set up here. We only set it up for the for our shard, so we only see that value in the shard. If you see previously, we had it for the chart in the net section, but for the config server, we didn't provide any extra configuration, so we are not able to see that information here. Okay, let's delete our database. We should be able to delete it properly without any issue because we haven't provided do not terminate here. So our database is deleted. The ports are terminating, so we have successfully deleted our shards. So that's all for chapter 1. Now we'll go to chapter 2. In chapter 2, we are going to talk about the day 2 operations. So for the prerequisite is you need a replica set deployed in your cluster. We don't have one as we have deleted the previous one. Let's deploy that first. We are deploying the same replica set that we have deployed earlier. As we have all the dependency available in the cluster, we are not applying those. We have just applied the MongoDB YAML, so it should bring up the cluster. Let's see what things we are going to see here. So first we are going to see version update. We'll see the version to be updated from 4.4.6 to another version 5.03. Then we'll see the horizontal scaling. Horizontal scaling means we will scale the replica. We'll scale the replica like you have you have 3 replicas, you can go to 4. You have 4 replicas, you can go to 3. Then there is vertical scaling. Vertical scaling means we want to scale the CPU and memory. Then there is reconfiguration. We want to configure the database. We have provided the mongod.conf. We want to edit the value. We can do that using the reconfigure. Then the reconfigure TLS will remove. We want to remove the or disable the TLS for our database. We can do that using reconfiguring TLS. Finally, volume expansion. We won't be able to see it today because it needs a real Kubernetes cluster with a storage class that has allowed volume expansion field true. If we see that our storage class, we have a storage class because it's standard. Also, the allowed volume expansion is false. So It's not enabled here because we are just using a dummy cluster. So it's not allowed here. But in your real cluster where you are using different kind of storage solutions, CSI driver, like Longhorn, etc., there you will be able to expand the volume. We'll just go over this to show you how it's done. Okay, now let's apply the version upgrade to YAML because it will take some. Okay, our database is ready, so we can apply our version update YAML. It's called ops request. We are going to talk about it. Let's update it first because it will take some time to apply it. We are going to watch it here. Okay, let's see the YAML of it. So as you can see, it's also under kubedb.com, but we have the ops prefix because it's day 2 operation. So in the kind, we are providing MongoDB ops request and providing it's a MongoDB ops request is the CID that's responsible for doing the day 2 operations. So if we apply this YAML, in the YAML, we are saying that this ops request is of type update version. And in the database reference, we are providing that we want to update this specific database, MongoDB replica set, and we want to make the target version as 5.0.3, which is currently 4.4.6. We are trying to update a major version. So from 4 we are going to 5. So if you apply this, our operator should do all the necessary things to update the database. So as you can see, it's currently the MongoDB obstacle status is progressing. If you see that it's trying to restart this pod, it's in pod initializing phase. So first, it will what it will do is we can actually check how it works. This is a simple configuration how it works. User first creates a MongoDB, then the MongoDB is watched by our provisioner operator, which creates the stateful set. Then user wants to update the version, then he create a MongoDB ops request to version upgrade. Our ops manager operator watches this and first it pauses the MongoDB. So why do we need to pause? Because when we are doing this operation, this is a critical operation for the database. As we have 2 operator, this is doing the works now. We have to pause the MongoDB so that the provisioner operator doesn't do anything. That means if the user changes in the YAML or something, the operator will try to make that happen here. But we don't want that because our ops manager operator is doing something to the database like updating the version. So we first pause the MongoDB. So while the database is paused, the provisioner operator can do anything to the database. Then the ops manager operator updates the database version of the stateful set and restarts the pods one by one. So how does it restart the pod? As you can see, it first restarted the secondary pods. This was the same before secondary, if you remember. This restarted, and finally it restarts this final pod. So as you can see, the first pod was our previous primary. If you check the role, it's now became a second standby because when it was restarted, election occurred, and this pod became the new primary, and it now joined the cluster with a new role like secondary. As you can see, our obstacle is successful. If we check here, after all the images updated and it performs some checks like everything is working properly or not, and it resumes the database finally and updates the images on the MongoDB itself. So if we check here, our version is upgraded from 4.4.6 to 5.0.3. We can verify it from all places. So let's verify. If we check the version from the MongoDB, we can see that the version says 5.0.3. We can check the images from the stateful set, which says that the MongoDB version is the image is of 5.0.3 image. Then we can check from the port, which also says the Mongo image is 5.0.3. Then finally, you can check it from the inside of the primary. So if we connect to the Mongo shell and run the db.version command, we can see that the db version is 5.0.3. So our database is updated successfully. We have successfully updated our database. We can actually see the data that we have inserted using Unity script. So we can see that the KubeCon database is here, even after the database upgrade. So if we, sorry, I have to use KubeCon. Then I have to use the find command. So we can see that the data we have inserted using the init script is already here. So even after the database is upgraded, we can actually find our data that we inserted previously. Our database is upgraded successfully. I can see a question on the Zoom chat. Can we do similar configuration for more than one replica for setting up Postgres database? Yes, of course, we can do that. Postgres database also supports clustering. So you can definitely use the Postgres clustering to set up similar configuration to use for more than one replica. So so we have successfully applied one ops request. Let's apply another, which is the horizontal scaling up. Let's apply it first. Let's exit from here first. We applied the horizontal scaling up operation. If we check the YML, we can see that it's similar to the update operation. We are providing a type as horizontal scaling. The database references the databases that we are using. And in the horizontal scaling section, I'm providing that we want 4 replicas of our database. As you can see, the horizontal scaling ops request is successful. Also, you can see that here there are now 4 replicas. One of them is primary and others are standby. We have successfully scaled our database.
So we just shared another poll question. You can let us know what was the most interesting learning in the workshop so far. You can just type it in the poll. So I see two questions in the chat. So the first is regarding the recordings. Yeah, so we will be sharing these on YouTube shortly. And the next one is for Mohammad. So Nikhil asks parameters for the DB selection and comparison of DBs in the cloud hosted and within the Kubernetes cluster was the highlight. Oh, okay. He's saying this is the learning. Okay, that's cool. Yep.
My operators are still in container creating stage. It's pulling all the images. I have to wait for a little bit. In the meantime, we can actually talk about the other kind of scaling. So we have already was still horizontal scaling. So we have 3 replicas. So we're using horizontal scaling. We can actually make it 4 replicas or scale down to 3 replicas, something like that. And in the vertical scaling, we can actually scale the CPUs and memories for our database. If we check out the vertical scaling of request YAML, vertical scaling of request YAML, we can see that the type is vertical scaling, similar to before, where we wanted to do horizontal scaling. We provided horizontal scaling type, and we provided a name of the database. Similar to that, we have one vertical scaling types, and we are providing the database reference here. And the vertical scaling ops request here, vertical scaling ops request here, we're providing the request and CPU that we want for our database ports. So if we see the current configuration in the replica set YML, we can see that our current pod template or replica has CPU of 100 millicore and a memory of 512 megabyte. And we want to change that to make it 1 GB of memory and 300 millicore of CPU. And we want to make the limit to 2 GB. So we can do that by applying this particular scaling ops request. Then there is reconfiguration ops request, which is also similar ops request. You can actually apply a reconfigure ops request YML. Here you can see that same as before, where we are providing the type as horizontal scaling. Here we are providing the type as reconfigure. Similar to before, we are providing a database reference, and in the configuration section, we are providing the max incoming connection as 3000, which we have provided before as 50,000. We are making it 30,000. So here we are providing that we want the MongoDB count to be a max incoming connection as 30,000. So our operator will merge the previous config with this one and make the value 50,000 as 30,000. Then there is another ops request for reconfiguring TLS, which is also a similar ops request. If we check here, if you check the YML of reconfigure TLS, you can see that we are providing the type as reconfigure TLS. We want to actually disable the TLS for our database, so we are providing TLS remove as true. So if we apply this, our TLS configuration will set up perfectly. PRS configuration will disable perfectly. And finally, there is the call volume expansion. Volume expansion means you want to expand the volume. Currently, you have 2 GB of data. Let's say you want 20 GB or 10 GB or 2 GB of data. And you can say that we are providing a mode here, which is, says offline. I've talked about it earlier. But online means your pod will stay running when you expand the volume. And offline means your pod will be down when you are applying the volume expansion. So this means that when offline expansion is happening, the pod actually unmounted from the volume actually unmounted from the pod. The pod gets deleted. Then the volume get expanded, and finally when the pod comes back, it claims the expanded PVC as its own, and then finally all the pod do the same, and all the volumes are expanded by the MongoDB ops request. So this actually depends on your CSI driver. Some CSI drivers support online volume expansion, some doesn't. If your CSI driver support volume expansion but doesn't support online expansion, you can still expand your volume using offline volume expansion. So that volume expansion. Our kubedb ports are up and running. I think I can apply the kubedb YAML now. Oh, I haven't installed cert managers. Not sure why the PMIS pooling became so slow.
So the question by Nikhil, he says, could you give some information on the upgrade strategy and staging used for stateful sets pod?
So the update strategy is rolling update and the sequential update. But the thing is, when you are using database, you cannot actually depend on those things. The problem is in databases, you have to uh, use your restart or you use your database, restart your database ports in a ordered fashion. So when you are going to restart, you have primary, you have secondary ports. So you have to first restart the secondary. But the stateful set update strategy doesn't know about which one is primary, which one is secondary. So it's you cannot actually depend on the update strategy of stateful set. So you have to use a operator or you have to do it manually when you are doing this. So when you are using operator, a database operator actually knows which pod is primary, which pod is secondary. So it can decide to which one to send the update first. So by this, you can actually do that, but you cannot depend on stateful set update strategy for the database. So I think our database is ready currently. Uh, took a lot of time. Sorry for that. So now let's skip a bit. The vertical scaling works similarly as the other obstacles. It just updates the pod resources. And the reconfiguration also works the same. You just restart the pod with different it just restarts the pod with their different configuration. Let's try this. If you want, you can try those two. Just follow the instruction here. You will be able to do that. I will just go skip to this as we don't have enough time. Just apply the reconfigured TLS. Let's watch this here. As you can see, our reconfigured TLS is in progressing. So it will restart all the database ports with disabling the TLS. In the meantime, we can talk about the next section, which is the database backup and restore. So to do the backup and restore, you will actually need to have a ST computable bucket, also add a replica set deployed in your cluster. So if you don't have a S3 bucket, don't worry, you can use Minio, which is a S3 computable storage. You can just use this command to install Minio. Here you can provide the root username and password of the Minio dashboard. Also, you can create a dashboard initially using this helm command. So I'll just do that. So I think our Minio cluster is installed. Here is the Minio. Okay, our reconfigured TLS obfuscate is also successful. Let's verify it. If we connect to the database, as you can see, we are able to connect without any TLS certificate that we have used previously. So we have successfully disabled the TLS in our database. We can also check the data that we have inserted via the init script. So we'll just use kubecon show collections .workshop.find. So as you can see, the data still exists here. So after the removing TLS, we can still connect to this and see the data. Now let's go to the next section, which is backup and restore. If you have successfully installed Minio, you can actually connect to the Minio dashboard if you port forward the Minio service. We have port forwarded the Minio service. Let's connect to the dashboard using the link. Yeah, as you can see, here is a object in the object browser. You can see a bucket called Mongo. Currently, there is no data. So if we want data in this object, backup our data here, we have to apply some YAMLs in our stash, which is called backup configuration and repository. So if you check the repository here, it's a S3 bucket. So if you check here that it provides the endpoint and it provides the bucket name that we have just created here and some region and prefix. So it will be to keep the backup here. And we need a storage secret name. If you check here, there is a storage secret. You have to edit this secret with your access key and secret key. Let's create some access key and secret key here. If you go here, access keys and generate access key, you can get the access key and secret key. Let's edit our storage secret. In the access key, provide the access key. And in the secret key, you have to provide the secret key. Let's verify we have provided it correctly for EY0, and it is MBNN. So we have provided it correctly. So let's save it and then we will apply it. Let's apply it. Applied it. We can create the repository also that we have seen now. Before that, before setting up backup, we can actually insert some data in our database so that we can see them backup and restore later. We connect to the database. Use kubecon. And we can run this script to insert 100 documents in the collection. So if we check this out, count, we can see that there are 100 documents in the participant collection. Now let's apply the backup configuration. I'm going to talk about the backup configuration a little bit. later. Let's trigger a backup. Let's watch the backup session here. We check the backup session. It's the phase is running. So what is backup configuration and backup session? So backup configuration is the backup specification where providing the schedule when to take the backup, the repository that we have created, the target to which to take backup of which database, and the return policy, what data we want to keep. So it will take backup in the provided schedule, but as we don't have time, we want to create a instant backup. So we are creating a backup session. Normally, it gets created by the operator by when the time schedule matches. Now we are want to create manually, so we just telling that the invoker is our backup configuration name. So it will create a backup. As you can see, our backup is succeeded. So you should see some data on the menu console. If you reload the browser, your object browser, you can see that there are some data here in our object browser. So we have successfully taken the backup. Let's exec into the database again and delete the KubeCon database so that we can simulate a disaster scenario. Sorry. Okay, we have dropped the database. If we check the show DBs, there is no database called KubeCon. So we want to actually restore it. So we need a restore session. So let's apply the restore session. If we apply the restore session, you will see that it's running. Also, you'll see that our database is now data restoring phase. And it's now succeeded. So we have successfully restored the database. Let's check that. So DBs, you can see that the KubeCon database came back. So if we check the data, we check the collections are here. We check the participants that we have inserted earlier. We can see that all the data is here. If you count the data, it should say 100. So, okay, we have successfully restored the data from our backup, even after we deleted it. So that's all for the backup and recovery session. There is another chapter called auto scaling. You can actually auto scale your database with applying this. Currently, you will need a metric server for this. So if you install the metric server, then if you check the current CPU and memory, you will see that you have 100 MB and 512 MB. 512 MB CPU and memory. So if we want to auto scale the database, just let's apply the auto scaler YML. The auto scaler YML is applied. So how does the auto scaler works? If you check how does the autoscaler works, I'm just giving a brief introduction. If you see here, the user creates a MongoDB and a provisioner does this thing. User creates a MongoDB autoscaler. Autoscaler creates some BPA, etc. to monitor the autoscaling operation. Then the autoscaler actually creates MongoDB ops request in the background to autoscale the database. So it monitors the database using the MongoDB autoscaler, and it gets some recommendation from the autoscaler that the database CPU needs to be this, database memory needs to be this. So finally, when all of this matches, it applies those using a MongoDB ops request. Finally, the database gets auto-scaled. As you can see, it already automatically created a ops request. It is now in progressing state. because the autoscaler thinks the database should vertically scale. If we check the vertical scaling of request or YML, we will be able to see you can see that in the vertical scaling section, it's providing that limit should be 400 MI and the memory should be this. So when the autoscaler creates this, the database gets automatically restarted. As you can see, the vertical obfuscate is also successful. So it successfully autoscaled all the data, all the nodes. If you check this, you can see that the data became 400 MI, which was previously 100 MI and 512 MI. We can also verify it from the stateful set. So it's also 400 MI. We can also check it from the pod. So it also reflects that the autoscaler suggested. So we have successfully autoscaled our database. So that's all for my side. If you have any question, you can ask. We only missed one portion, which is the reconfigure. We actually did all other things. We did horizontal scaling. We did vertical scaling, not directly, but as you can see, it created a vertical scaling object and vertically scaled the database, but it was auto scaling because you didn't trigger it manually. So we did that too. We just missed the reconfiguration ops request. You can try that yourself. You just apply the YML. You will see that the data gets changed. We also checked out reconfigure TLS. We cannot check the volume expansion because we don't kind doesn't support allowed volume expansion too. That's why we cannot see that. But if you have a real Kubernetes cluster which has a CSI driver that supports volume expansion, you can actually try that too. So if you have any questions, you can ask.